Just check a bit. I'm just changing the slide. Can you hear? Can you see the next slide? Or you're still seeing the first slide?
Yes.
Just go back because sometimes there are problem. Okay. Anyway, I will keep it like this so in that way it will be easy for me to. Okay. So good afternoon, everyone. Today, in the last class, we have already started talking about nanomaterials and a bit history about nanomaterials and where the nanomaterial terms came from and a couple of applications of nanomaterials. Now, in today's class, what we will do is we will try to go for a couple of preparation methods, how these nanomaterials can be made. We will, because we have done the classification, if you can remember from the last class, we have done depending on how many dimensions are in the not in the nano range. Depending on that, we have actually categorized the nanomaterials into basically 0D, 1D, 2D, and 3D materials. Okay, we have talked about it if you can remember from the last class. So in today's class we will try to see, depending on these categorizations, we will try to see what are the preparation techniques that are easily available to us, which actually enable us to make these nanomaterials. Okay, just go back. Okay, so here is a brief overview about what are the different techniques that are available for different dimensionality of the nanomaterials and different classes of nanomaterials. Okay, so as we have already talked about that there are 0D, 1D or 2D, even 3D basically. 3D where we do have composites. We will talk about it obviously in today's class as well for the preparation techniques. And if you look at these different classes over here, so you do have the discrete nano objects, you have surface nano featured materials, which is class 2, and then you do have class 3, which is nothing but termed as bulk nanostructured materials. So if you look at the first box over here, this is a box where you are using or you are trying to make nanomaterials which are like discrete objects, so like nanoparticles that we have talked about, because 0D is if you could remember, these are basically nanoparticles that falls into this category where all the dimensions, that is x, y, z, all the dimensions falls within the nano range. That means it is within 1 to 100 nanometer. Okay, so for those materials, you can either use the gas phase condensation or gas phase uh, processes, or you can use the liquid phase processes. We will talk about it within a couple of minutes. So there are inert gas condensation, evaporation, colloidal methods that are available. Colloidal methods are basically the liquid phase processes where you have we will talk about it also later on in the class. But I'm sure you have started noticing that now we are moving towards, because this course is about colloid and surface engineering, right? Now we are talking about the nanomaterials. There might be a confusion why we are actually doing that. If you look at this structure over here or look at this over here, this says that colloidal methods are actually basically used over here in order to make 0D class 1 nanomaterials. Okay, that is the basic idea of doing or putting nanomaterials into this course. Uh, Obviously, for class 2, you can go whenever you try to make certain surface manufactured materials with 0D. nanomaterials. They You talk about the physical or chemical vapor deposition techniques. When you go for the bulk nanomaterials, you are either go for cryomilling, condensation of nanoparticle by sintering, equi angle extrusion. All these methods are available. Okay, for 1D, mostly it's the directional growth from the catalyst dots and templating. Uh, for class 2, we will talk about this with 1D material. This is widely used method of making nanomaterials, and that is basically lithographic methods. And this lithographic method is basically used for making electronic uh, microchips or electronic circuits, all these things. Okay, so we will discuss this technique in much more details, but not in today's class, in the next class. But other methods we will try to discuss in this class itself. Okay, so class 3 materials is incorporation of nanotubes and rods into polymers or metal matrices. Then you do have 2D materials, where we will talk about the beating, then electro deposition, PVD, CVD, that is the physical vapor deposition, chemical vapor deposition, self-assembled films, all these things. We will also talk about for class 2 also, you can use similar kind of methods in order to produce surface featured nanomaterials, as well as you could use rotating shutter, PVD and CVD, cyclic electro deposition, in order to make bulk nanostructured materials. Now, whenever we talk about the bulk nanostructured materials, they are mostly either composite materials, or you either use it for large scale. I mean, you are making it in the bulk quantity. Okay. Also, sometimes it is due to the for the industrial application. Sometimes we use these class 3 nanomaterials. Now, let us just move towards what are the different methods of making 0D nanomaterials. We have already talked about it. We said that there are two different processes. Either you can go for gas phase processes or liquid phase processes. So in the gas phase process, there are mainly two methods which are widely available, or which are widely used rather. This is inert gas condensation and inert gas expansion, whereas for liquid phase processes, which can also be termed as colloidal processes, which use the surface forces to create nanoscale particles and structures. And there you can either use ultrasonic dispersion, sol gel methods, methods relying on self-assembly. All these things we can talk about. Now let us just go ahead and look one by one all these methods, and try to see the basic understanding of it. We will not go into much details of it because of the time constraint. Rather, what we will do is we will try to just get a basic idea of what all these processes does, and then what are the basic differences between them. If you know a bit of working principle, you will obviously differentiate between different methods that are basically used for different nanomaterial preparation. Okay, so the first one is basically the inert gas condensation method. In this particular case, is basically an organic material is basically vaporized inside a vacuum chamber, and inert gas, either helium or argon, is periodically admitted to this vacuum chamber that is available over here. Okay, and the source vapor can be an evaporation boat, a sputtering target, or a laser ablation target. Either of them. So this is basically the evaporation sources. And from here, the inert gas is basically introduced to the vacuum chamber. And once the atoms basically boils off, they quickly lose their energy by colliding with the inert gases, and the vapor cools rapidly and supersaturates to form nanoparticles with the size range of 2 to 100 nanometer, and then they form this cluster of nanomaterials on the cold finger. Okay, and with the help of a scraper you can just take out these clusters, and then you can collect it at a collection tray at the bottom of the vacuum chamber. And here also you maintain a certain inert atmosphere and inert atmosphere. Okay, and and you can basically further process these materials once you collect it. Now the main disadvantage of this kind of process, even when we will talk about the the next one, that is basically the inert gas expansion process also, here in it is very difficult. Most of the time, it is difficult to control the size of the clusters, because what happens is there are two steps basically are there in these particular processes. First one is nucleus formation, and once the nucleation starts, it will actually, what will happen is it starts forming some clusters. Okay, atom by atom deposition on these surfaces, which will actually form clusters, and uh, in a way that they lose their boundaries and they actually fuse together to form a single molecule. Like that way, it at the beginning it will start, and after certain time, the surface energy of these clusters are such that it cannot further form the collapse together to form the collapse together for and uh, uh, rather they actually uh, they become as it is. I mean, they don't coalesce together. Okay, rather they try to aggregate. That means they maintain their they maintain their size boundaries over there, but they try to cluster together, they try to aggregate together. That's how it happens. And then these aggregates you are basically collecting by scraping off with the help of a scraper at the top of the vacuum chamber. Okay, and this is how it goes. So the main disadvantage is basically the particle, as the particle forms, they tend to cluster and increase their size, defeating the original objective of actually making a nanomaterials. So if we can maintain a proper evaporation rate with the certain temperature of the cold finger, and scraping off after a certain time, that means the time of scraping from this um, cold finger actually gives you a better size, control of better size. I mean, controlling the size of the nanomaterials in a better way. Okay, in that way we can do that. Next is inert gas, that is free jet expansion. Uh, Today's class will be a, I mean, everything will be descriptive, even next week as well. After that, we will go to these forces where you will find out some mathematics that will be probably more interesting to you. Please bear with me for this descriptive things, but try to just get an glimpse of what are the different techniques available for nanomaterial preparation. Okay, so it is basically also the similar kind of operation. But here, rather than condensation, which happens in the first case, here the basically the expansion is happened. Okay, so basically the evaporated atoms are basically carried out by a high pressure helium gas stream that is expanded from a nozzle. This is the nozzle from which this gas stream has been expanded into a low pressure chamber at a supersonic velocity. The adiabatic expansion of the gas leads to the sudden cooling, causing the evaporated atoms to form these clusters over here. And these clusters then collected in a collection tray. And obviously, Here also you do have an inert atmosphere that has been maintained, and agglomeration is also a general problem in this particular case, where which we have seen for the inert gas condensation. So rather than condensation of the vapor that is happening in this particular case, here basically you are getting I mean, the aggregates are formed, or the clusters are not aggregates, rather clusters are formed due to the expansion of this vapor through this nozzle to a low pressure zone. Okay, and this is the evaporation sources where you put certain metals or certain alloys. If you want to make certain composites, then you have to put two different components in these two different evaporation sources, so that the cluster formation happens with two different components. And uh, these methods can be used for any material which doesn't decompose at very high temperature. Okay, so that is the advantage of these methods, but the basic disadvantage is being aggregation or agglomeration of nanoparticles. Okay, now the next process, which is probably a couple of you have already been used, if some of you are actually using or doing a project on nanomaterial preparation or application of nanomaterials. So this is basically sonochemical process where ultrasound has been employed. The range of ultrasound is in the range of 15 kilohertz to 1 gigahertz for nucleation of a chemical reaction to takes place. Okay, now in this particular case also there are two steps. First one is nucleation, and second one is cluster formation, and then finally you form the collisions, and then finally you get this nanoparticle in clustered form or aggregated form. Okay, and basically magnetorestrictive or piezoelectric transducers used to generate the ultrasonic wave with a wavelength of 1 to 10,000 microns in a liquid filled reaction vessels. There is no direct coupling of the acoustic field with the chemical spaces happen in this particular case, because these are not at the molecular level. Okay, and the reaction basically happens due to the cavitation formation. The tensile, if you look at this ultrasonic sound wave, it looks something like this. Okay, there is a tensile part, and there is a compression part. So the tensile part of the wave actually pull the liquid apart to form a tiny cavity, and the compression part of the wave basically compresses it, whereas some reactants vaporize inside it. When the next tensile wave re-expands the bubble, it oscillates in volume at frequency of the sound waves and pumping it up as more vapor enters during the expansion part of the cycle. When this bubble reaches to a critical size, it collapses. Now, this collapse is basically happens in adiabatic. Uh, because the collapse rate is very high, and there is no time for heat flow, generating these tiny cavities or tiny localized heat spots, which are having a temperature of around 5,000 degrees Celsius, and sometimes the pressures are around 2,000 atmospheres. And these hot spots basically becomes the reaction zones for nucleation to occur in this particular sonochemical process. And that's how you actually create the nanomaterial. And these reaction spots are so small that you can actually create nanoparticles as small as 2 nanomaterial with this kind of techniques. Okay, these are basically a probe sonicator kind of arrangement, where you do have an ultrasonic horn, and then you do have a probe over here through which through kind of a nozzle kind of thing, and through which basically the ultrasound waves are disseminates to the salt solution. Uh, this technique basically can be used to produce a large volume of material for industrial application. Now, if you go to certain industries for nanomaterial preparations, you will find that they use sonochemical processing or sonochemical method in order to produce nanomaterials. And although the price is still on the higher range, but still, I mean, because the time requirement for nanomaterial preparation is so less in this particular method, sometimes that basically, although the power requirement is quite high, it basically, nullify I mean, not nullify, but it basically, subs- it basically I mean, there is a trade-off basically between the time and power requirement, and this method basically is more energy sensitive, but time requirement is much lower compared to other conventional methods. And also, this can be actually scaled up to industry use, whereas the other methods are still not, I mean, those methods that we have already talked about, that inert gas condensation and inert gas expansion, still they are not in a way useful for the industry, that means for bulk nanomaterial preparation. Then there is a salt gel deposition technique. This is basically a chemical technique, a colloidal technique rather, to prepare the nanomaterials or synthesize the nanomaterials, where you do have a precursor solution. That is, most often it is a metal oxide solution. Like here, example is given for titanium isoprop oxide. If you are producing titanium dioxide nanomaterial, and then the precursor basically goes for the hydrolyzation and polymerization reaction to form colloidal dispersion, or this is basically known as sol. If you just directly do the precipitation and dry it, you will obtain discrete nanoparticles, which are in the range of even 10 to, I mean, depending on your metal alkoxide and reaction parameters, you can obtain nanomaterials ranging below 10 nanometer as well, but mostly it is 10 nanometer to 100 nanometer range you can obtain the nanomaterials. And obviously you can tune the shape of the nanomaterial depending on the reaction parameters. And if you further treat this sol and by chemical treatment, uh, by making it kind of a super polymer, where one enormous molecule in the form of an open 3D network has been formed, which is known as basically gel. And then if you go for solvent evaporation, you will obtain nanoporous membrane kind of structures in this particular case. Gels are something like this discrete nano particle that you can see over here. They try to sling together to form a large molecule, okay, kind of a network structure. And you all of you know what is a gel. I mean, even if you just see the Vaseline petroleum jelly, that is basically a gel, okay. So that kind of structure actually has been formed, and if you evaporate it, you will obtain nanoporous membrane structures. And these sol gel methods are mostly used for a wide variety of materials, including paints, ceramics, cosmetics, detergents, cells, all these things. You can use any kind of metal oxide. You can use even two different metal oxide to produce nanocomposites, nanoporous membrane with different two or three different, nanometries structure. Hey, it's audible, right? না আমি একাই বলে যাচ্ছি আর সবাই ঘুমিয়ে যাচ্ছে?
It's audible.
Yeah, okay.
Audible, ma'am.
Okay, thank you. Okay, next is molecular self-assembly. Again, these are, again, we are talking about, still we are talking about the 0D nanomaterials over here. Either class 1, class 2, or class 3 structures. But when we talk about the molecular self-assembly, I mean, it is also very, very widely used. Okay, so basically, if you just look at this over here, the basic idea behind molecular self-assembly is the spontaneous association of molecules under equilibrium conditions into stable, structurally well-defined molecules. Okay, so molecular self-assembly uh, is, it is already available in nature. There are so many different applications of molecular self-assembly. If you just take a sugar solution, okay, and you go on adding sugar in it, and the first when the supersaturation happens, obviously the first crystal of sugar that starts taking place, or crystallization starts taking place. And once after the onset, you will see that there is an increase in crystallization. Okay, that is basically or formation of more structure, I mean, uh, larger number of larger molecules, or larger crystalline structures. And that is basically an example of molecular self-assembly. And if you look at the in terms of the nano range molecular self-assembly, all of you, because of the COVID pandemic, all of you have already seen the structure of DNA, because in the paper, in the news media, everywhere, we talked about how the DNAs can be modified in order to fight the COVID-19 sometimes. So all of us, even, I mean, plus 12, some of you have biology, so you know that the DNA structure, that is basically a classical example of molecular self-assembly. In the nature, it is already there. What we try to do is we are trying to mimic those structures in this artificially. Okay, whether it is at all possible or not. I didn't come up with certain structures where you can see very good pictures of molecular self assembly assembled nanoparticles, where you do have this spherical structure, you do have cylindrical structures, all these things. Rather, over here, what we will talk about is how we can use those molecular self-assembled structure in order to create 0D nanomaterials. Okay, uh, so basically, this is suppose you put certain surfactant, amphiphilic surfactants. Amphiphilic means, or amphiphilic molecules, is basically one end, it does have hydrophobic head, and another side, it is hydrophilic in nature. Okay, so one side hydrophobic, one side hydrophilic. So if they can arrange themselves such a way, you put it into water, so what they will do is they will try to create this kind of structures, with hydrophilic going to the water side, and the hydrophobic going to the other side. Okay, in that way they try to create this kind of self-assembled uh, uh, you know self-assembled structures, and the core of these structures can be used for nanomaterial preparation. And if you can prepare the nanomaterial within this course by center of the missile, because these are known as missiles, and this center of the missiles, if you can use it for reaction, then you can create nanomaterials with you know uh, size of probably 200 nanometers. Okay, depending on the obviously the thermodynamics. Thermodynamics solution thermodynamics does play a great role over here in this particular case, but we are not going into the details of all these things. This is one of the example of self-assembled nanomaterial preparation. Then another one is a classical example of Langmuir-Blodgett technique, where we actually use Langmuir-Blodgett film on top of water. So surfactant, again, if you are taking it surfactant, you put some water, and which is having amphiphilic surfactants, which is having a hydrophilic head and hydrophobic tail. Then they, when you put that on the surface of the water, they will try to create uh, you know uh, a monolayer of those surfactants. Okay, and with this Langmuir-Blodgett technique, you can push those molecules in one side, and by that way you can create a dense single monolayer or single layer, that is a monolayer formation of a film of these surfactants. And if you put a substrate within this Langmuir-Blodgett uh, you know instrument, and you push it down, which is having a, a, a let us consider this, which is having basically a hydrophilic nature, and then if you push it into the water, so once you take it out from there, this fatty acid or the surfactant monolayers basically try to climb through this substrate, and you get a layer deposited on this substrate. Okay, this is how you actually create a film of substrate, or a monolayer on the substrate that you are actually trying to coat with a nano film. Okay, in that way you can do that. Okay, so probably I will show you when we will talk about the different forces and all these things. There we will talk about Langmuir-Blodgett film in much more detail. How, what are the forces that actually works in this particular technique? Those things in that discussion, probably it will be much clear to you. And I will also show you one picture of Langmuir-Blodgett instrument. Okay. So these are the methods that actually made uh, use of 0D nanomaterial preparation. Then we will move to methods for making 1D and 2D nanomaterials. The first one is a very crude technique, which is foil beating, which is also sometimes known as gliding. And this basically is known, gliding is the art of applying gold leaf to a surface, which has been known from the ancient ages. And I mean, because gold is a very, very expensive material, there are obvious incentives to use as little of it as possible. Okay, and basically, this gold leaf is made by beating the metal into uniformly thin foil, roughly around 100 nanometer thick. So that's why it falls into this category, and it is just applied by smoothing it onto the adhesive coated surface of the object that needs to be glided. That is it. This is simply uh, hammering gold on top of a adhesive coated surface that you want to coat with a certain 100 nanometer thick gold plating, okay, or gold leaf. Then next one is electro deposition. So in electro deposition, what is this is also all of us know it. I mean, uh, all of you already have talked about or know what is electro deposition, but we can carefully, we can carefully, handle this electrodeposition so as to create a very very thin layer that is around 5 millimeter. I mean, uh, from couple of nanometers to even up to 5 millimeter, which actually requires no further processing. If we can create a smooth surface by on the substrate of substrate by using electrodeposition, okay, and that is basically very very useful in certain cases, because most often, although we are talking about the uh, uh, nano range, sometimes we need a very very thick coating on top of certain substrate, okay, but these coatings, even if it is this deposits, even if it is nano, it is in millimeter range. If you can go up to millimeter range with electrodeposition, but these are basically, this layer is nanocrystalline in nature, mostly for electrodeposition, and that's why it actually falls under the category of 1D or 2D nanomaterial preparation. Okay, so basically you do have an anode and a cathode and the electrolyte. You basically, by using the electric charge, you basically create or you basically deposit uh, the desired metal on top of your substrate, okay, and that this layer thickness is simply depends on the current density that you are using and the time for which the current flows. And this deposit can be detached if the substrate is chosen to be soluble by dissolving it away. Okay, so if you certainly choose a substrate which can be dissolved within a certain material or solvent, then you can have this nanocrystalline uh, layer as it is without the substrate. Sometimes we require the substrate to be coated, sometimes we require only this layer, that is a nanocrystalline deposit layer, and that we can obtain simply by dissolving the electrolytes. It's simply by dissolving the substrate, that you have to choose wisely during your application or operation. And obviously this process is relatively cheap and fast, and it allows complex shapes. Okay, so this is how we actually can generate the nanocrystalline deposits. Then these techniques are very very important. um, Physical vapor deposition, and next slide I will talk about the chemical vapor deposition. These techniques are widely used for nanomaterial preparation, and uh, I mean, still, although I have said that these are widely used nanomaterial for nanomaterial preparation, but you have to understand that still it is not actually mostly industrially used, because these techniques are still very very expensive, and uh, mostly for research purposes and to make certain object which you can actually buy it with a very very high price. There you can use this PVD and CVD techniques. uh, but nowadays the price has been lowered mostly, and the people started using in the industry as well for certain purposes, certain special purposes for PVD. Okay, so in PVT plating, basically, a thin layer of material, which is usually a metal, is deposited from a vapor onto the object that needs to be coated. Okay, so you look at the top of the chamber, there is the substrate, and at the bottom you have this evaporant that needs to be actually deposited on the substrate, and you do have a heater over here. Now you just heat it up. Okay, so the vapor is basically being created in a vacuum chamber by directly heating it, or either by electron beam heating of the metal, and this basically condenses onto the bot condenses onto the coal substrate, and that is basically physical vapor deposition. Now, in this particular case, there is no chemical reaction that has happened, uh, or simply the material that is being evaporated from the bottom has been deposited on the top of the substrate. On top where the substrate has been placed. Now, if you can remember, if you can just correlate it, you can correlate it simply with your like when you take a hot shower, what will happen if you have a mirror inside your bathroom? So there is a layer of condensing um, con- uh, condensing vapor that has been formed on the top of the mirror. Okay, you cannot see it. So that's the same thing that happens in this particular case. And in PVD plating, there is no potential differences between the bath and the workpiece, and when we are using the PVT ion plating, the vapor is basically ionized and accelerated by the field, by the electric field. And in PVT sputtering, argon ions are accelerated by electric field onto a metal target and ejecting ions onto the component surface. And by introducing a reactive gas, you can basically create a compound. Okay, so a simple example of that, if you sputter titanium in an atmosphere of nitrogen, it actually gives you a coating of titanium nitride, TiN. Okay, so like that way you can actually use the physical vapor deposition, although there are directly no chemical reaction that is been taking place in this particular case. এখন আবার কি আসতে চাইছে? কেউ কি এন্টার করতে চাইছে? হুম। Okay. Okay, so here, if you look at the bottom that has been actually mentioned, almost any metal or compound that doesn't decompose chemically can be sputtered, making this a very flexible process. Targets can be changed during the process, allowing it to make you a multilayer to be built up on a certain substrate, and these multilayers can have remarkable mechanical and electronic properties. So all these variations are possible with physical vapor deposition. Okay. So next one is chemical vapor deposition. It is almost similar kind of, um, phenomena, but in this particular case, the reactant gas mixture
Madam, slides is not visible.
It is not visible. Yes, it's visible.
Now, okay.
দেখা যাচ্ছে তো?
হ্যাঁ হ্যাঁ
Okay. আমি আসলে ওইটাই ছিলাম দেখি। Okay. Now for chemical vapor deposition, uh, if you look at over here at the bottom, there are two gas in. So the reactant gas mixtures are basically brought in into contact with the surfaces that needs to be coated, where it decomposes, depositing a dense pure layer of metal or a compound. Okay, and either the deposit can be formed by a reaction between the precursor gases in the vapor phase, or by the reaction between the vapor and the surface of the substrate itself. Okay, there are two possibilities in this particular case. And for this process, the main disadvantage is that it often require a very high temperature for these gases to react. Okay, and sometimes the reaction temperature is 800 degrees Celsius, and sometimes there are processes where we require a temperature of 1000. I mean 1200 degrees Celsius, as well as some processes for making artificial diamonds we go around 1800 degrees Celsius. So but this technique is a very useful technique in order to actually create nanomaterials uh, with chosen mechanical and mechanical properties. So actually, there are conventional CVDs, and there are some now there are new techniques that is coming up with time, which are basically moderate temperature CVDs, which is known as MT-CVD, and metal organic precursors are basically used in this particular case, and temperature becomes as low as 500 degrees Celsius. Okay. Um, and if the chemical reaction in the vapor phase are activated by the creation of plasma, then that process is known as plasma assisted CVD. If the laser beam actually shine through the reacting gas mixture in order to create the reaction hotspots, and in order to create the reactions, or rather catalyze the reactions, then that process basically is known as laser CVD. So there are whole set of new techniques that are coming up day by day with these conventional techniques. And as I was mentioning, you can use this chemical vapor deposition in order to, and create artificial diamonds. Probably a lot of you have known that the diamonds now can be created in the lab, and that this is a basic method of creating artificial diamonds. And the coatings that are in this particular case, also you actually get a coating on your substrate, and these coatings which are formed with PCVD, then
What is the composition of this diamond, artificial diamond? You said.
the composition is basically, they just start with the graphite. Okay, they try to put the graphite in the I mean there are certain cases where they have different reaction gases, reacting gases that are available. But sometimes the substrate that they use started with any kind of uh, inert substrates, but sometimes they use graphite. By using the physical vapor deposition, also they create diamond. Okay, not always that this is chemical vapor deposition, but for physical vapor deposition they use graphite, that I know. For chemical vapor deposition, I'm not completely sure about it. I have to look at it and I can come back to you. Okay.
Okay, ma'am.
But by using physical vapor deposition, they use graphite as their starting material, and they actually vaporize it. And with a certain substrate, they can actually get the molecules atom by atom actually deposition on the top of the surface, and in that way you actually create the diamond structure. There are very good sites available, not sites, even YouTube videos are available where in the labs they are making these artificial diamonds. If you want to, you can just have a look at it.
Okay.
Okay. So the coatings that are formed with PCVD methods are typically nanocrystalline or amorphous because of their formation is no longer dependent on the equilibrium thermodynamic constraints. Okay, so that is why these chemical vapor depositions are very important in order to create certain nanocrystalline uh, coatings. But again, this chemical vapor deposition is again a very uh, uh, energy intensive and very expensive technique. I mean, all the techniques that we are talking about for nanomaterial preparations are mostly um, expensive till now. But when we talk about the lithography, you will see that although I mean they are not as expensive as this CVD or PVD techniques, but they are more use. That's why they are more useful, and they can create nanostructures. We will talk about it in the next class. Okay. So now we are moving towards the methods for making 3D nanomaterials rather than 1D or 2D nanomaterials. For 3D nanomaterials, if you just look at this figure over here, you can see that there are mainly two approaches. One is top-down approach, and another one is bottom approach, and obviously there is an intermediate approach. Okay, so in the top-down approach, what happens is you do have a macro scale material available to you. And the structure in such a way that it does have a macro or millimeter kind of structure. That crystalline structure is like that way. But if you put it into some some mechanical or uh, yeah rather mechanical techniques, then you can create bulk nanostructured materials, where we will see that these are the equi-angle extrusion and rapid solidification takes I mean uh, does create nanostructured materials from these macro or millimeter range materials. Uh, the diameters always remain, most of the epi-angle extrusions, they remain same. But what happens is they actually uh, alters the grain structure. Okay, so from the grain structure from the macro range, it becomes in the nano range. We will see within, I mean, next one itself we will try to see that. Then there is this intermediate cases or intermediate processes where you do have mechanical alloying or micro machining in order to create the bulk nanostructured materials from micro or micro range. Then you do have the uh, bottom up approach where you are actually using the you are basically using the molecules in order to atom by atom deposition or atom by atom creation in order to go for the cluster, and then you go for the bulk nanostructure solids. This kind of approach, that is a bottom up approach, we already have talked about all these things a lot in detail, like inert gas condensation, solvent, and self assembly. From there you can create the structures, and from these structures you can create certain nanomaterial by using certain methods that we will discuss over here. Okay, but these techniques already have been discussed previously.
And when this bulk nanostructure solid is means produced by stacking the molecules.
Yes, yes, stacking the molecules. You will see that there are certain compression or uh, casting or sintering methods, which actually, by using those methods, you can get these bulk nanostructured materials. Okay.
Means manufacturing, various manufacturing methods in yeah, in nano domain, means in micro
Yes.
domain.
Yes.
Mhm.
Nano domain. But here, whenever we talked about the bulk nanostructured materials, the structure itself is in nano range. That is, the grain sizes are in the nano range, but the actual bulk material might have a bigger, higher, I mean, larger size. Okay, it's possible. We will see in the next example itself, next process itself. Okay, not in the next process, but next to next process itself, we do have that kind of example. Okay, so okay, now why it is important that we need to make the 3D nanomaterials, or rather that bulk nanostructure solids. Like all of you know that sometimes the materials that get their properties are basically due to deposition of something or incorporation of certain nanomaterials into their structure. Like if you probably all of you have a bit idea, those who are from mechanical background does have an idea about high strength low alloy steels, right? They basically get their strength from nano dispersed carbides. Okay, so this is why it is very important that you understand what are the methods of making 3D nanomaterials. Now, also, if you go for the alloys that are used for the aerospace, which are based mostly the aluminum, magnesium, and titanium based, they are basically strengthened by the precipitates with this dimension range of 10 to 100 nanometer. If you just bulk in the bulk range, if you just mix it, you didn't have that kind of strength that requires for aerospace application. But if you go for a deposition in the nano range, that is 10 to 100 nanometer, then only you can obtain that kind of strength into those alloys. Okay. There is another example like the copper alloy wearing connectors that are basically used in automobiles and other electrical equipments. They retain their spring, and how do I call it, springiness basically. That means it maintains its spring kind of formation, uh, maintaining that good electrical contact, because the copper beryllium nanoparticles has been used. Okay, so all these things, if you talk about, they are bulk material, but due to the incorporation of certain nanomaterials in it, their properties has been enhanced. Okay, that is the purpose of making these 3D bulk nanomaterials. Okay, so the first process of these top-down processes that we will discuss over here is the rapid solidification process. দেখা যাচ্ছে তো তোমাদের ওটাতে? Okay, হ্যাঁ, আচ্ছা,
হ্যাঁ স্যার, হ্যাঁ ম্যাম।
হ্যাঁ, thank you. So the first one is rapid solidification process, where basically the idea is basically, you if you cool the material at a very normal rates, most of the solids, or most of the liquids, they solidify to give solids with large crystals or grains. But in this particular case, the trick in making nanocrystalline or the amorphous material is just to cast them uh, in such a manner that you deprive the material of the time, so that it transform from the, I mean within no time you just transform that liquid into solid. Okay, so instantly if you can do that, then obviously it will not get time for creating the larger grains, and in that way you will obtain nanocrystalline or amorphous materials out of it. Okay, one example that has been provided in this particular case is melt spinning. There they allows cooling rates of up to 1 million degrees centigrade per second. You can imagine that. And this is basically enough to freeze in the liquid structure in certain alloys, giving amorphous or crystalline wares or ribbons. Okay, so this is how we can actually obtain this kind of uh, uh, I mean, rapid solidification can be achieved. Then there is also another process where in the second picture, where the laser surface hardening has been taking place, where is a laser beam basically melts on top of a substrate, okay, which is then cools very fast due to conduction, because the substrate is already at is already cold. Okay, so you are just melting the top of the surface and it is solidifying immediately, and that is the idea behind it, and that's how you obtain a material with a nanocrystalline surface or amorphous surface. Okay, so we move to the next one. Okay, I was talking about that, you can create nanograin out of micrograins, and this is a classic example or classic technique of doing it, which is known as equi angle extrusion. This is basically used, uh, sorry, not away. This is away, not away, but away for of generating extreme deformation that you can think of while suppressing the fracture. Okay, so a rod is basically forced through the die, is savagely sheared and extruded, emerging as a rod with the same diameter as that with which it has been started, but a much refined structure. And if you go on doing this for several times, you will obtain these these materials with nanostructured grains rather than a microstructured grains. That is it. And this process becomes a standard one for making metals with grain sizes in the range of 100 to 500 nanometer range. Okay, so you are simply extruding a material with a high shear, or you just uh, uh, you know uh, you just put with uh, in the extrusion you put an angle so that the grain sizes become from the micrometer range it becomes nanometer range. That is how it does.
Ma'am, why
Yes.
it named equiangle?
Okay, it's basically equiangle is that means uh, this angle mostly is around 120 degrees. Okay, so this angle is basically at 120 degree. That means you are, if you are just creating a kind of a hexagonal structure, then you actually get this, all these angles become equilateral. Okay, so that means you just you can have an arrangement where you have one leg over here, another leg another side, another leg another side. All these angles are uh, equal in nature, as well as these angles are mostly 120, depending on obviously your grain sizes. I'm not saying that it is strictly 120, but usually it is 120 in nature. And because these angles are equilateral to each other, that is why this is known as equiangle extrusion. Okay.
Okay.
Yes, ma'am. Thank you.
Okay, so then I think we will talk about the other processes in the next class because it's already 5:40. I will not hold you much more because there are certain processes which we need to talk, micro machining and all, and nanoprofiling. And nanoprofiling, we will talk about the lithography. Uh, okay, so these intermediate processes we will start in the next class, and we will talk about the nanoprofiling as well. That is a top-down approach.
Okay, ma'am. Okay.
Okay, ma'am.
Okay,
Thank you, ma'am.
so
Okay, ma'am. Thank you, ma'am.
okay,
That
so
will-
I will leave
Thank you,
you
ma'am.
for the day, and we will talk about all these things in the next class.
We'll find the book also that is being shared.
Sound,
Yes,
please.
I
Okay.
will share it, and I will just share the notes as well. I will put everything on the classroom. Sorry, I didn't do in the last week, but last week's notes as well as this week's notes, I will put it on in the classroom. Okay, up to this.
Ma'am, is it new
Thank you.
subject?
Which one is new subject?
Colloidal and surface engineering.
Yes, in a sense, we actually offer from chemical engineering and subject known as interfacial engineering for chemical engineers only. And that subject is, I don't have to think about much because we go with the flow, right? That is mostly the interfacial phenomena, the forces. When I go to the forces, those, portions are similar. But here, these portions are a bit new for me as well. And
Ma'am,
this is the new subject, open elective. Yes.
ma'am, somewhere along the course, like as we are going through, can you please like give us some references on like how the questions can come because we have no idea of how
Yes, ma'am. That's
things.
what I was going to say.
Yes.
Means theory based or problem based.
Okay. So till now, whatever I'm teaching is theory, right? So these parts will be theory based. But when we go to the forces, then there will be problems as well as numeric. I mean numericals as well as some derivations and some understanding about different things. That will be more interesting to you when I go that side. Actually, I'm just waiting, Shashwata sir, to finish the first module of your course so that you have an basics understanding about colloids, and then we can go for those surface energy and then all those molecular forces, how it is interacting, where those properties comes from, those things. It requires a base, so that's why I'm just waiting for him to complete it, that portion.
Okay, ma'am.
Okay, but I mean, with due time, I will just give you some glimpses of what kind of questions can arise. Okay.
Yes, ma'am, that would be very helpful, ma'am. Thank you, ma'am.
Okay. Okay, so thank you all of you.
Thank you, ma'am.
Thank you, ma'am.
Okay, ma'am. Thank you, ma'am.
And next week also the same link. Okay, আমি আর next week এটা করছি না, announce
আচ্ছা
করবো
ম্যাম,
না,
আচ্ছা
but
ম্যাম।
same link. Okay.
Okay, ma'am. Okay, ma'am.
ঠিক আছে।
হুম